In a generalized Dicke model, a system of three-level atoms interact dipolarly with a single mode of an electromagnetic field, featuring three atomic configurations: Xi, Lambda, and V. The matter contribution is represented by a U(3) group structure, and a natural SU(2) subalgebra is constructed for each configuration using linear combinations of matter operators. 2 SU(2) local rotations decouple the M-dipolar interaction between two atomic levels, leading to an effective Hamiltonian consisting of a two-level Dicke model plus an isolated atomic level, and a remnant term corresponding to a one-body matter interaction. In the Lambda and V configurations, the one-body matter interaction disappears when two atomic energy levels are degenerate, resulting in a constant of motion that vanishes for the ground state. The authors utilize fidelity and susceptibility to determine the quantum phase diagram for a finite quantum system with a fixed number of atoms, detecting abrupt changes in the system state when a control parameter is varied. The phase diagram remains invariant under local SU(2) rotations, as the minima of the fidelity remain at the same loci. The Hamiltonian of the system is given by equation 1, where the matter operators obey in SU(3) algebra defined by equation 2. Rotations through the third element in each SU(2) subalgebra, shown in Table 1, eliminate the interaction between one pair of atomic levels with the EM field in the cavity. The transformed Hamiltonian, H, is expressed in equation 6, where the transformed frequencies and coupling constants are denoted with a tilde. This new Hamiltonian enables effective storage of quantum information in the generalized Dicke model via simple rotation. The research proposes a novel method for storing quantum information in a generalized Dicke model using simple rotations. This approach eliminates the coupling of the M field with a pair of atomic levels, introducing a new matter one-body coupling between atomic levels without a dipolar transition. The process is demonstrated in the lambda configuration, where rotations isolate specific atomic levels, enabling the exchange of information between qubits. The fidelity between the qubits is exactly 1, ensuring that information stored in one qubit can be retrieved by the other. This method can also be applied to the V configuration but not in the Xi configuration due to its population characteristics. The Hamiltonian is reduced to an effective Raman transition of a two-level Dicke model plus an isolated atomic level, with eigenstates obtained through numerical diagonalization. The research discusses storing quantum information in a generalized Dicke model via simple rotations, involving quantum Rabi oscillations in qubits formed by levels omega-2 and omega-3, with the stored information retrieved by switching to Rabi oscillations in the qubit omega-1 and omega-3. Numerical results show the robustness of this method, even with non-degenerate atomic levels. The research paper explores the concept of storing quantum information in a generalized Dicke model through a simple rotation, focusing on three atomic configurations: Xi, Lambda, and V. To understand the phase diagram of the system, the fidelity between neighboring states is calculated using equation 11, which allows for the detection of abrupt changes in the ground state as control parameters are varied. The phase diagram for the Xi configuration is presented in Figure 4, showcasing the minimum of the fidelity between neighboring states in both resonant and non-resonant cases. The results are compared with the separatrix obtained from a variational solution using coherent states as test functions, given by equation 13. The paper also discusses how the phase diagram remains invariant under SU(2) rotations, even when these depend on control parameters. This invariance is demonstrated in Figs. 46, where the stability and equilibrium properties are shown to be the same for the original and rotated Hamiltonians. The expectation values of the atomic populations are depicted in Fig. 3, illustrating the negligible population of uncoupled levels. The methodology for retrieving stored quantum information in atomic systems interacting dipolarly with a one-mode radiation field is proposed. It focuses on the generalized Dicke model and the use of a simple rotation applied to the Hamiltonian. The study explores various atomic configurations, including the Xi and V configurations, analyzing their separatrix shapes as a function of the number of atoms and detuning values. Figures 4, 5, and 6 provide detailed illustrations of these separatrix shapes for different atomic configurations and detuning conditions. The results show that as the number of atoms increases, the quantum separatrix tends towards the variational solution, indicating a stable transition from the normal to the collective region. The methodology's robustness is demonstrated through numerical examples, including the atomic V configuration under non-equal detuning, where the population fidelity is less than 1. However, as the system approaches resonance, the fidelity between states approaches 1, suggesting a high degree of accuracy in retrieving stored quantum information. The research discusses the storage of quantum information in a generalized Dicke model using a simple rotation. It begins by introducing the concept of a rotation operator and derives differential equations for transformed atomic transition operators. The authors solve these equations to obtain explicit expressions for the transformed operators, which are valid for an n-dimensional algebra. The transformations are applied to different atomic configurations, such as the Xi, Lambda, and V configurations, each with its own specific rotation defined by the forbidden atomic transition. The paper also presents a graphical representation of the separatrix for atoms in the Lambda configuration, comparing the quantum separatrix with the corresponding variational solution. For an appropriate value of alpha, one may eliminate one term of the matter-field interaction in the three-level Dicke model with a single electromagnetic mode, which has implications for the storage of quantum information. The research concludes with acknowledgments and provides an appendix detailing the rotation of the three-level Dicke Hamiltonian for arbitrary alpha. The research paper discusses the storage of quantum information in a generalized Dicke model through a simple rotation. This approach involves applying a unitary transformation to the Hamiltonian of the system, resulting in the invariance of the ground state diagram for certain special rotations. The authors focus on the concept of a simple rotation as a means to store quantum information within the generalized Dicke model. The paper references several previous studies on the Dicke model, including its application to quantum phase transitions and symmetry groups. The references provide context and background information on the theoretical foundations of the research. The paper also includes a list of references that further elucidate the concepts discussed, spanning multiple decades and covering topics such as quantum mechanics, symmetry groups, and quantum phase transitions. Overall, the paper presents a novel approach to storing quantum information using a simple rotation in a generalized Dicke model, contributing to the ongoing efforts in understanding and developing quantum computing technologies.